All right, this is the second and final hour of Physics 1B for September 27th. All right, one other thing, we just talked about specific heat. Again, specific heat controls, how much does the temperature change of an object based on the amount of heat that you add. Or you could use it in the other way. You could say, given a certain temperature change, how much heat must have been added to create that. A couple other things to mention about it before we start looking at some examples. If you have an infinitesimal heat change, dq, and an infinitesimal temperature change, dt, then you can also use this expression. We will need to use this expression quite a bit in this class to do certain things. Specifically when we're talking about kind of like raising the temperature of something very, very, very slowly, we're going to use this equation. We'll use this equation in one of the problems we do here in a second too. There's also something you're going to be confronted with as well, which is what's called molar heat capacity. So we can use the same concept of how much material do you need to get a certain temperature change, but instead of using mass, we can use number of moles. So this equation says that suppose that I add some amount of heat to a system and I know the number of moles of the system, then you can use capital C. This stands for capital C and little c. There's so little difference between them, so I apologize for that, but the capital C here is the molar heat capacity. Those are listed up here in this table. So there you see molar heat capacity, and you see molar mass. Molar mass is something that can be, this is in kilograms per mole. I believe molar mass you can find from the periodic table, right? Something that's going to come up a lot in this class. Does that sound right to y'all? You can find molar mass from the periodic table. Yeah, right? Okay. And in case you all, again, I know a lot of you haven't actually taken chemistry, so I'll just show you what's meant by that. In the periodic table, there are numbers. There's what's called the atomic number. Let's see if we can find a nice pick. This is a good one. This is a bad one. Why would it not have, wait, do we do lists with properties? Okay, seriously? All right, what's a good periodic table? Nope. Nope. This one looks like it might work. So much information here, but this is a good one. So let's look at aluminum. Where's aluminum? Aluminum's right here. There we go. Aluminum has an atomic number of 13. Does anyone remind me, what does that mean? What does the 13 mean? This stuff actually is going to be important in this class. You're going to need to know how to read the periodic table. What's 13? Number of protons the element has, exactly. Okay, and then you've got Al, which is obviously the symbol we use for aluminum. And then you have this number, 26.982, right there. Might be kind of hard to read. And every one of the elements has this number. It increases as the elements get larger and larger and larger. And this is the molar mass. This is the amount of grams of the substance that you need. 26.982 grams of aluminum gives you 1 mole of aluminum. Okay, that's the molar mass. But it's in grams, so 27 grams would be 0.027 kilograms, which, if you come to this table, is how it's written right here, 0.027. 0.027. So that came from the periodic table. The numbers on the periodic table are in grams per mole. I just noticed I didn't finish writing this equation down here. Okay, so we've got molar mass, that's part of the equation, and then we've got molar heat capacity over here, all right? So molar heat capacity is going to be the heat capacity in joules per mole Kelvin, which is why you need to multiply by number of moles. Oh, the other thing I was going to say is, what is a mole? As I'm sure some people do not know. What is 1 mole? Maybe nobody knows. Maybe everyone's asleep. Both of those things are possible, right? What is a mole? Some of you know. There's a lot of people typing. Isn't it Avogadro's number or something? It's related to Avogadro's number. So what's Avogadro's number? It's 6.022 times 10 to the 23. So 1 mole is 6.022 times 10 to the 23. What goes right here? Let's fill in the blank. This is Avogadro's number, that's right. 6.022 times 10 to the 23 is Avogadro's number. That's right. I know that even if you took chemistry, you probably don't remember what goes here, but 100%, you need. This is the kind of stuff that this book is going to expect that you know. I'm going to expect that you know this stuff too. I feel like this is basic science stuff that you have to really kind of know this stuff to do. Well, as soon as we start using the word mole, you got to know what a mole is, right? Come on, someone has to know the answer. Amount of particles of a substance. So it's 6.022 times 10 to the 3 atoms, basically. I think it could be something other than atoms. It could be molecules. I think amount of particles of a substance is probably good. But usually this is what I think of it as. It's 6.022 times 10 to the 23 atoms. But I suppose it could be molecules or particles or something else here, I guess. Usually this is the way it's written. Okay. All right, so that's a mole, molar heat capacity. And you can solve this as shown in these steps right here to show that the molar heat capacity C is equal to the molar mass M multiplied by the specific heat C. So they're related to each other. And if you do that, then, yeah. All right, so just another way that this might show up. I noticed this picture right here, which is definitely something I should have mentioned earlier. Water has a much higher specific heat than glass, so something that's probably very obvious to you is if I take a big pot, let's say you're going to make spaghetti or something, and you take a big pot of water, you put it on the stove, you fill it up with water. It takes a long time for the water to heat up, but the pot that you put it in, it heats up really quickly when you put it on the stove, right? That's another factor of specific heat. Okay, I think we know enough here now to solve a couple of problems before we talk about phase changes and how that affects things. If we can get through all that stuff today, I'll be very happy. So, a couple of specific heat problems. We're going to go through these relatively quickly because these first few are going to be pretty simple, but we're going to get a lot of practice with specific heat, so it's just going to kind of get progressively more difficult. So just stick with me here, and if you get confused at any point, let me know. All right, this says, during a bout with the flu, an 80-kilogram man ran a fever of 39 degrees Celsius, which would be 102.2 degrees Fahrenheit, instead of the normal body temperature of 37, which is about 98.6 degrees Fahrenheit. Assuming the human body is mostly water, how much heat is required to raise his temperature by this amount? So we have a person. We're saying the person is basically made of water, okay? And we start off with an initial temperature of 37 degrees Celsius. And the person gets a fever that causes their body to heat up, as you all know happens with fevers, up to a temperature of 39 degrees Celsius. And we know that the mass of this person is 80 kilograms. And we want to figure out how much heat is required to raise his temperature by this amount. So we can use our equation, which says that Q is equal to mass times specific heat times delta T. Q is the thing we're solving for, so this is purely a plug-and-chug problem. We plug in 80 kilograms for his mass. Specific heat C is the specific heat of water, which we go back to our table. You'll get pretty used to using this one. 4190. I worry about using this particular value, but it should work. I always use 4186, but I think your book likes to use 4190, so you're probably going to want to use that. If you have to use something different in a problem, it'll probably tell you. This is joules per degree, joules per kilogram per Kelvin. We're going to multiply it by a change in temperature. The change in temperature in this case is delta T is equal to 39 degrees Celsius minus 37 degrees Celsius, which is 2 degrees Celsius change. Whoops. 2 degrees Celsius change, which is the same thing as 2 Kelvin when we're talking about the change in temperature. So you can use either one. We'll use Kelvin, so change in temperature is 2 Kelvin. And then we just, whoops, scroll down a little bit so you can see that. So there we go, there's our equation, and then we just plug in, or we solve for our answer, so it's what, 160 times this? So I got 4190 times that, you get 670,000. I'll answer that question in just a second. Tell me if you get the same answer. I got 670,400. Yeah, so 670,000 joules, or I like the way you put the answer there, that's better. We could write it as 670 kilojoules. Looks a lot nicer than writing a bunch of zeros. A little easier to understand what that means. All right, so you said we're not adding 273. Well, let's do it. What would happen if we did that? So if we add 273 to 39, then that would be 312 Kelvin. And then if we added 273 to 37, we have 310. So you get 2 Kelvin. Okay. Doesn't mean it's a bad question, Troy, because I'm sure other people had the same question. All right, so yep, change in temperature in Celsius and Kelvin will always be the same because 1 degree Kelvin and 1 degree Celsius mean the same thing. Even though we don't say degree Kelvin, we just say 1 Kelvin. All right, so that is super simple example, just designed to show you how this equation might work. Yeah, I don't know. Let's do one that's a little trickier, and then we'll go into the phase change stuff where it gets. Oh, we can do both of these. Let's do this one first. All right. Heat is really important in electronics, as I'm sure anyone here who works with electronics knows. Meaning, if you have a phone or a computer. You're designing an electronic circuit element made of 23 milligrams of silicon. So we have 23 milligrams. That's going to be a mass, right? We'll just write that's a mass. And it says of silicon. That's going to look weird if I write it like that. We'll just say silicon down here. All right. The electric current through it, so it's a circuit, and it says the electric current through it adds energy at a rate of 7.4 megawatts. Okay, so we have 7.4 megawatts. Milliwatts, sorry. 7.4 milliwatts is the rate of energy added. Okay. We'll just say rate of energy flow into the system. The idea is you have a circuit, there's electric current flowing through it. Electric current is a flow of electrons, and that flow of electrons through any material causes the electrons to rub against the material, which causes the material to heat up. This is part of why your phone will heat up if you have it running like a game or a movie for a long period of time. Your phone will heat up, right? Sometimes also phones might heat up if you're charging them, when depending on how they're made. Anyway, point is electricity causes things to heat up. It's a major part of how we design things. It says if your design doesn't allow any heat transfer out of the element, so we're assuming that all the heat that goes in stays in the system. Most electronic systems are designed so that they let heat out. But it says at what rate does its temperature increase? The specific heat of silicon, we can write this down, is 705 joules per kilogram Kelvin. All right. So what are we trying to find? What rate does its temperature increase? That's what we're trying to figure out. Okay? So we've got some circuit. It's got electricity flowing through it. And we know that it causes 7.4 megawatts of energy to flow in. And our question is, what is the temperature increase? Or the rate of temperature increase? Ugh, I'm so bad at... Ugh. Okay. What temperature does the... at what rate does the temperature increase? Now, in this problem, I'm just going to say from the beginning that instead of using this version of the equation, although maybe there's a way we could use it, what we need to figure out is not just the flat temperature increase, but the rate at which it's increasing, right? So there's really two ways that you could do this. We could change this equation. If I was teaching Physics 2a, this is what I would say. We could say that this Q is a quantity of heat that goes in, and it goes in at some rate, delta T, and that should be equal to mass times the heat capacity times the change in temperature. So basically what I could do is I could say, if I divide both sides of this equation by delta T, then this would be the quantity that we're solving for. And I can go back and say that this, the 7.4 milliwatts, sorry, would be the rate of energy flow into the system, right? And we would basically be saying, what is this equal to? This is what we would be solving for. Okay, does that make sense as a way of doing it? Watts is joules per second, right? So you just take joules, which is Q, and you divide by time. Sorry, this looks like that's a capital T. It's supposed to be a lowercase t. Sorry about that. That should be a lowercase t. Okay, but yeah, so now what we could do, Matthew, is to do it in the version, like the way that, this is the way your textbook does it. It says, well, let's say that we define the amount of energy that flows into our system to be dq, right? And then what we do in this case is we just divide by dt. It's literally the exact same thing, though. And I find that the boxed purple version is simpler. I don't know what you all find simpler, but either way, you're doing the exact same thing. Delta D, who cares, right? Is the amount of watts pointing towards the circuit 7.4? Oh, it's milliwatts? Yeah, I don't know. Sorry, this is just a... Sorry, I didn't mean to be confusing. That's milliwatts, yeah. All right, so let's solve it. Let's use this version, I guess. So what we're going to do is we're going to say that this is dq dt. Is there any difference between these two? I guess. I guess if we did some calculus, there would be. And then we'll say that what we're looking for is this quantity right here. That's what we're trying to solve for. So what we get is that. And we plug in the numbers that we have. So 7.4 milliwatts goes in for this one. So that's 0.0074 joules. I'll write it as joules per second. Times 1 divided by, the mass was 23 milligrams, which would be 0.0... Oh, we need to put this in kilograms, actually. So we'll write it as 23 times 10 to the negative 6 kilograms. Is that right? You'd multiply by 1,000 mg in 1 gram, and you'd multiply by 1,000. Yeah, that's right. You have to divide by that. Yeah. Okay. Well, it's 23 e minus 6 or 2.3 e minus 5, right? However you want to write it, it's the same thing. I wrote 23. There's no decimal. Okay, and we also have to divide by the specific heat, which was 705 joules over kg Kelvin. Okay, didn't go off the screen yet. And all of that should be equal to the rate at which the temperature changes. Plugging all that in together. I probably said way more than I needed to in this problem. Sometimes I just like to go through the simpler explanation, but in this case it maybe made things more complicated. I don't know. So that number divided by 23 minus 6 divided by 705. Oops. Okay, what do you all get? I got a pretty small number. Actually, it's not a small number. Yeah. You got 0.045, are you sure? 0.45. That's what I got to. 0.46, really. We'll write it as 0.456. That's going to be Kelvin per second. But it would be the same thing in degrees Celsius. That's a pretty big number if you think about it, right? If your system is heating up at a rate of about 0.5 Celsius per second, right? After a minute, it will have heated up by 30 degrees Celsius, which is almost 100 degrees Fahrenheit. That's a lot. It's a lot. The reality is, if this is how your system was designed, it would melt. The whole system would just start to melt after a couple minutes, right? So as a result, with electronics, one of the important things you have to think about is how do you dump heat out of the system? And there's different ways that we do this. How do you do that? How do you get the heat out of a system like, let's say you're talking about a computer or a cell phone or whatever you're talking about? How do you get the heat out? Heat sinks and fans. Yeah, that's right. Boy, everyone answered that question real fast. That's good. Yeah, so things like heat sinks. What's a heat sink? Well, we'll talk more about that later, but a heat sink is basically a bunch of pieces of metal that are kind of like a bunch of blades of metal all in a row that are designed to have a large surface area. They're a metal, so they do a good job of releasing energy, and that's what a heat sink is. The thermal paste, I think, makes sure that there's good thermal contact, right? So that the heat flows directly into whatever you're trying to dump it into. So, as you all mentioned, there's fans, but there's also coolers. You can have like liquid cooling and things like this. Yeah. Okay, so you have to have some way of getting rid of the heat, otherwise your system will heat up indefinitely, and of course, heat can destroy your electronic components. Okay, let's do one more problem that doesn't involve phase change, and then we're going to do one problem with phase change. Hopefully we can do this before class ends. I don't know. We'll try. We have to go a little bit faster. Okay, so let's talk about calorimetry. Okay. For calorimetry, what we're going to do is we're going to say, suppose we have a bunch of different materials, and they're all subjected to heat being added or removed. How does that affect the total heat change that happens in the system? And I'm going to say that what we're going to do is we're going to sum over all of the different heats that go in, and that this should be equal to 0, okay? So this is for multiple substances. Multiple substances in thermal contact. Now, I don't know a better way to talk about what calorimetry is than to just do a problem. I don't know. I'm not going to go into details about like which is the one we can do. Where did it go? Did I already copy it down here? Maybe I did. This one. This one. Where did it go? We can't do this one. We can't do this one because they have phase changes. I must have deleted it by accident. I don't know. Okay, it's on the other slide, so that's fine. I come back up here. Go to here. This one. Come on. Copy. Okay. Paste. All right. So, calorimetry. Sum of all the heat changes equal to 0. Keeping in mind that this can be positive or negative, just like with forces, even though heat is a scalar. All right, so a temperature change with no phase change. A camper pours, let me make this big enough so you can see it, 0.3 kilograms of coffee initially in a pot at 70 degrees Celsius into a 0.12 kilogram aluminum cup at 20 degrees Celsius. What is the equilibrium temperature? Assuming that coffee has the same specific heat of water and that no heat is exchanged with surroundings. Pretty big assumption there. No heat is exchanged with surroundings. Okay, so we have a closed system. In our closed system, that's super interesting. You're saying people learned about Higgs things real quick when Xboxes would red ring, aka stop working. People stacked pennies on the Xbox as a heatsink and fixed it. That's so funny. They literally just stacked rows of pennies on top of it to help it to dump heat. That actually worked. I mean, it makes sense that it works. I'm surprised. Yes, sir. Fred had like 30 pennies on his. Only 30. Wouldn't you want to go even bigger? Just dump like a ton of pennies on there? That is really fascinating. I had never heard about that. I do remember Xboxes having the red ring. I had friends that did that. Yeah, I mean, pieces. This isn't like something. We're literally going to talk about it probably next week. But yeah, like if you look inside of your computer, if you have a computer, a desktop, even if you have a laptop and you open it up, you will find these things that are literally like effectively the same thing as pennies. You see these rows of. I gotta keep going. I don't want to get too distracted. Anyway, so we have 0.3 kilograms of coffee that starts off. What's the best way to draw this? Eventually, it's all going to end up in the same cup, right? So we have a cup. It's an aluminum cup. So this is our aluminum cup. It says that it starts off with an initial temperature of 20 degrees Celsius. So the initial temperature of our cup I'm going to call that the initial temperature of the aluminum, like this, is equal to 20 degrees Celsius. We're going to pour coffee that is 70 degrees Celsius into the cup. Oh, and the mass of the aluminum is 0.12 kg. All right, so we're going to pour coffee in here. Here, I'll make the coffee blue. And what we know about the coffee is that its initial temperature, T initial for the coffee, I'll just put C for coffee, is equal to 70 degrees Celsius. And we also know what the mass of the coffee is. We'll say mass of coffee is 0.3 kilograms, just right here. And I believe that's all the information that we have. So the coffee is poured into the cup. The cup starts off with an initial temperature of 20 degrees Celsius. The coffee starts off with a temperature of 70 degrees Celsius. And our goal is to figure out what is the equilibrium temperature. That is to say, after time has elapsed, what is the final temperature of my system going to be equal to? And we're going to assume that the energy is not lost to the environment, okay? Energy stays within our little system right here. So this whole thing is isolated from the environment. So we'd have to have some kind of a top to it, right? In addition, we'd also have to have the entire thing surrounded by styrofoam. So our aluminum cup would have to be an insulating cup of some kind that has a top to it in order for this to make any sense. But let's assume we can imagine that, okay? In fact, let's put a top on it. Put a top right here, and then I'm just to make this a little more realistic, let's assume that the cup itself has styrofoam here, okay? So this is going to be insulation. Could be something like styrofoam. Just to make this a little more realistic, because it is impossible that an aluminum cup wouldn't transfer energy to its environment. All right, so it's covered. There's insulation here, and what we're interested in figuring out is what happens with the cup itself and the coffee. Just those two things. We're not going to worry about the styrofoam, even though styrofoam also has specific heat. We're just going to ignore it. We're going to assume that it creates perfect insulation, so that the whole system remains closed. There's no heat transfer in or out. That means we can say that if we sum up all of the individual heat transfers that occur in our system, they should sum to 0, which means we're going to take the heat transfer associated with the coffee. We're going to add to that the heat transfer associated with the aluminum, and those should add to 0, which means one of these has to be positive and one of these has to be negative. And since the coffee is the thing that's cooling down, I think this will be negative. The aluminum is the thing that's heating up. This will probably be positive. All right, so we write in here our equations. For this case, it's just going to be our specific heat equation, which says that if I take the mass of the coffee multiplied by the specific heat of coffee multiplied by the change in temperature for the coffee, plus the same thing for the aluminum. So mass of the aluminum plus specific heat of aluminum. No, oops, not plus. Multiplied by specific heat aluminum multiplied by the change in temperature for the aluminum. This should add to 0. Start writing over here so we can use more of the space. So let's see, do we want to plug in numbers? We can't plug in numbers yet. So we'll go MC, CC. Delta T coffee is going to be the final temperature. I'm going to call the final temperature just T since it's going to, I don't want to write a bunch of subscripts. So T is going to be the final temperature minus the initial temperature of the coffee. T, how do I write? Yeah, T initial coffee plus the mass of the aluminum times specific heat of aluminum times the final temperature of the aluminum, which is the same for both, and then the initial temperature of the aluminum here. And our goal here is to solve, all of this is equal to 0. Our goal of this is to solve for capital T. So in the interest of time, I'm going to make a bunch of algebra steps here, and I'm going to see if you can follow along. So if I want to solve for T in this equation, what I'm going to get is I'll just tell you what I did. So I want to isolate this variable here, right? T. So what you do is you do a distribution, you multiply through. You're going to get MC, CC times negative T naught C. We're going to add that to the right-hand side. That's this term right here. You're going to get a MAL, CAL, T naught AL term. Add that to the right-hand side. That shows up right here. What you're going to be left with is just MCT and MCT for both of these. You factor out the T and then divide by the coefficient. Again, we're running out of time, and I want to talk about latent heat. So we're just going to let you work out the details of this later. If you all think I made a mistake, let me know, but I think that's correct. And then we'll scroll down and plug in our numbers. So we get, okay, mass of coffee was 0.3. Specific heat of coffee, they said to use the specific heat of water in the problem. Assume that coffee has the same specific heat of water. We'll just convert everything to Kelvin. So let's see. The initial temperature of the coffee, T naught C, would be, you add 273 to this, so that would be 343 Kelvin. I don't think, you actually don't need to convert the things to Kelvin. The initial temperature of the aluminum would then be 393 Kelvin. You can put this in Celsius, you get the same answer, and I'll show you that in a second. But, okay, T initial for the coffee, that's here. Plus, mass of aluminum is 0.12. I'm going to run out of room. Specific heat of aluminum, we got to get from the table. I think it was 910 maybe. Yep, 910. Apologize, these things look so small. I don't know what else to do. And then we multiply by the temperature, which is 393. If I make this any bigger, it'll take up the entire screen. I don't think it even matters, Matthew, in this type of problem. I'll show you why. Okay, and then the bottom, we just have the same kind of thing repeated. So 0.3 kilograms, 4190. God, I hate writing these units so much. I don't like things to be sloppy, and they always come out sloppy. And then we do 0.12 kg, and then 910 J over kg K. We did it. Wrote the whole equation out. Yay. Is it blocked off? A little bit. So we'll scroll down some. And we end up getting temperature is equal to. You all tell me what you get out of that. Yeah, you can check in this problem. You're going to get the same. You get the same answer if you use Kelvin or Celsius, I'm pretty sure. I think. We'll find out. Do that math right? 273 plus 70 would be 343, right? Yeah. And, oh, this one's wrong. This should have been 293, right? 273 plus 20 is 293. Yeah, okay. So that should have been a 2. That same 2 is going to show up. Let me erase it here. Here? That's the only place. I'll just put it in red. I made a mistake. That's 293. So I got 340, 339, which actually seems pretty reasonable. Because it needs to be in between both numbers. So this is a totally reasonable answer. 339 Kelvin would be, if I subtract 273, I got 66. And the question is, if I go back and I redo the equations, but I use the same numbers, let's see. So I'm going to redo this, but I'm going to put things in Celsius. So 343 would become 70 plus 0.12. 293 become 20. You get the same answer whether you put this in Kelvin or Celsius. And the reason why, Matthew, is not because the negatives, it's because this is a change in temperature in this problem that we're calculating. And delta T has to be the same for Kelvin and for Celsius no matter what. Does that make sense? So when you're doing your specific heat problems, while it's never going to be wrong to convert to Kelvin. Just keep this in mind. It's never going to be wrong to convert to Kelvin. So when you're not sure, like on an exam, just convert things to Kelvin. Okay. But when you're talking about this change in temperature, it will be the same whether it's Kelvin or Celsius. So if you think about it, it's a good way to check your work, right? To do the problem in Celsius and do the problem in Kelvin and make sure you get the same answer. And if you don't, you probably made a mistake. Like I just did. I just made a mistake, right? I thought this was 393. And if I had solved the problem using that, and then I solved the problem using Celsius, I would realize I would get two different answers, and then that can't be right? So that's our answer. Does anyone have any questions about what we just did? Have a lot of you seen this before? Probably a lot of people have seen this before, I would guess. But so I guess I'm more interested in the people that have not seen this before. Did this make sense? If you have not taken chemistry, if you didn't do this in physics 2A, if you didn't do this in high school, does what we did make sense? The process is pretty straightforward. It does look complicated, Kelvin, exactly. But ultimately what you're doing is quite simple. I think that the hardest part of this probably is putting this in your calculator. Ultimately. I think. Maybe I'm wrong. It can get even more confusing too. So just keep in mind what we're doing here. At the end of the day, the equation we used was basically this, along with the definition of specific heat. Okay? And that allows us to find the temperature they come to. You can always use your brain with this stuff too and say 70 degrees Celsius, 20 degrees Celsius. Certainly the final temperature has to be somewhere in between. And in fact it is. And you'll notice something else here that happened. The final temperature is much closer to the initial temperature of the coffee. Why is that? Why is the final temperature so much closer to the temperature of the coffee? This should be pretty reasonable too, before you even answer. Take a metal cup that's at room temperature, 20 degrees Celsius, right? Pour coffee into it. It's not surprising that the cup is going to be very, very hot after some amount of time, right? Not too surprising, right? So why is it that the final temperature, conceptually, is closer to the temperature of the coffee than the temperature of the aluminum? What's the conceptual reason for that? Okay, that's part of it, is there's more coffee. Yep. But the biggest reason is because coffee has a higher specific heat. Much higher. Almost more than 4 times as big, right? More than 4 times as big. So that means the energy associated with the coffee at 70 degrees Celsius is kind of a lot more than the energy of the aluminum at 20 degrees Celsius. And the aluminum will obviously be able to... So water holds heat really well. That's important to understand. It holds heat really well. That can then be transferred. Okay, the last final thing that I want to talk to you all about today is what happens when temperature change... Sorry, what happens when a phase change happens. So we need all of these. I don't know that we'll be able to do both of these problems, but maybe we can do one. Probably have to go over a little if we do that. All right, so a lot of graphs and stuff, but we'll just start with this. Just this definition right here. All right, so when an object undergoes a phase change, what happens to its temperature? What happens to the temperature of water when it goes from ice to water? What happens to it? What happens to the temperature of water when it goes from ice to water? I take a cup of water, right? I put ice into it. I put ice into the water, right? After some amount of time, I have a combination of ice and water. What's the temperature of ice water? What is the temperature of ice water? Kohler, that's not an answer. What is the temperature? I don't want a relative term. I want an answer. What's the temperature of ice water? I have ice and water in a container. What would the temperature be? Some of the ice is melted, but there's still ice in there. 32 degrees Fahrenheit, right? Yeah. 0 degrees Celsius. Both correct answers, right? If I have a combination of ice and water, so I have a container, and inside of the container I have liquid water, but I also have ice. And of course the ice is going to melt because it's in liquid water, right? The combination is going to have a temperature that's equal to 0 degrees Celsius. This is ice water. And as the ice melts, right, the temperature will not change. Now, I'm skipping over some details. It's because all the ice is not melted. That's right, Pat. Probably near the bottom here, the temperature is probably not exactly 0 degrees Celsius, right? But near the ice, the water is certainly going to be about 0 degrees Celsius. Now, if we can completely isolate our container so it can't exchange any energy with the environment, then the whole temperature is going to be 0. So, as the ice melts, the temperature doesn't change, right? So if I want to talk now, without a doubt, as the ice is melting, there is energy coming in to melt the ice, right? I mean, it's not just going to stay ice forever. It's eventually going to turn into just water, at which point the whole system is going to start heating up in temperature, right? Everyone agree with that? It will not stay ice forever, and eventually it will heat up. But as long as there is ice in there, the temperature is not going to change. So we know that energy is coming in. We know that the ice is melting. And we want to be able to quantify exactly how much energy you need to melt the ice. And for that, we use this equation. We call this latent heat, or the L is called latent heat in this equation. It says the heat transfer associated with a phase change Q is equal to M, which is the mass of the substance, multiplied by the latent heat for this phase change, L, latent. Latent stands for hidden heat. It can be positive or negative. If the heat enters the material, it's positive. If heat leaves the material, it's negative. Okay? Now, that is a really simple equation, really, right? It's M times L. Well, what's L? Well, for L, we have to come to this right here. And these are the heats of fusion and vaporization. So this is associated with melting and boiling, all right? There's a lot of information on this table, so let's take it one at a time. Let's just look at water. Water is right here. All right, let's look at the normal melting point. We know the melting point of water is at either 273 Kelvin or at 0 degrees Celsius, okay? And the heat of fusion is 334 times 10 to the 3 joules per kilogram, okay? So for water, the latent heat of fusion is 334 times 10 to the 3 joules per kilogram. What this means is you need to put in 3,340 joules to melt 1 kilogram. Is it really only that much? Yeah, I guess so. You have to put in, so if I have a piece of ice, right? I have ice, and let's say it's 1 kilogram of ice. I have to add 3,340 joules of heat in order for the ice to turn from ice into water. That's what it takes. It takes 3,340 joules of heat to turn ice into water. Ah, yeah, that seems so small. I knew that couldn't be right. I'm silly. Yeah, it's yeah. Okay. 334,000 times 10 to the 3. All right, thank you for correcting me there. I appreciate that. That seems so wrong. Yeah, okay, so you need 3.34 times 10 to the 5 joules. That's what you need in order to melt the ice. Okay. Now, what's the temperature going to be while this is occurring? The temperature is going to be 0 degrees Celsius. So latent heat refers to the transfer of heat that occurs during a phase change, during which the temperature does not change. Okay? The temperature will change above and below the ice point. Does that make sense? That's what latent heat is. The energy needed to make a phase change. Yep. A phase change is from gas to liquid to solid. We call those phases, yeah. State of matter or phase. There's also latent heat of vaporization right here. So again, if we look at water, we can see that the boiling point of water, 100 degrees Celsius or 373 Kelvin, and this is how much energy you need to turn water into steam. It's actually almost a factor of 1,000 more than what you need for water, because you see there's an extra digit right here. To go from to go from ice to water, you only need this much energy, but to go from water to water vapor, you need this much energy. And that's a lot, right? It's a lot of energy. Shouldn't be too surprising. If you try to boil water on your stove, it takes a long time, right? Probably takes like 3 to 5 minutes to boil a cup of water on your stove. Yeah, it takes time, and it takes energy. And during that time, what happens to the temperature of the water? So let's compare this to what we said before. Let's scroll this down. So let's say that I'm heating something up on a stove. So I have a stove right here, and above that stove I've got some kind of a grill, and on top of that I put a pot, and in this pot I have water, and it starts to boil. What's the temperature going to be? As the water boils, does it go over 100 degrees Celsius? Does it stay at 100? Is it lower than 100 while it's boiling? It stays at 100, exactly. So does this make sense? The idea is that we know heat is going in because it's boiling and because this thing has to stay on. And what happens to the boiling water if you turn the heat off? Does it continue to boil? Or does it stop boiling? What happens if you turn the heat off? Simmers? That's not a very scientific thing to say. It's either boiling or it's not boiling. Simmering is something you'd say about cooking. Good answer, though. It stops, right? You can try this for yourself. Get some water, put it on the stove, right? Turn the heat on. Now, this isn't going to work on an electric stove. Not as well, at least. But it will work. I guess with the electric stove, you can just take it off, right? Okay, so turn off the heat. If you have an electric stove, you have to take the pot off. And I promise you that while you would see bubbles, the moment that the heat is removed, the bubbles stop, right? And it stops boiling almost instantly. And that's because it's already at 100 degrees Celsius. The energy that you're adding to the system is basically freeing the molecules from the surface of the fluid and turning them into water vapor, right? All right, so the key thing to understand here is during a phase change, temperature does not change. During a phase change, temperature does not change, but there is energy that is either added or taken away depending on what direction you're going. It's 11:31. There's no way we can finish this. We can't do a problem. We'll have to do it next time. God, I hate having 1 hour of 2 hours of lecture a week. It's so hard to cover anything and go slow enough so that I feel like I'm still somewhat connecting with you all and trying to interact with you. I will leave you with this picture though. We'll do a problem next time. That's too bad. These are the harder ones, but what we could do actually, that never works. Maybe I can record something. Maybe I'll just record something. This is a picture of the phase of water changing as it goes through different things. There's a lot happening on this graph, and I think it's a little bit hard to read, but just highlighting the things that you can understand from this. Temperature increases as you go up on the y-axis here. That's the temperature axis. So you have a vessel of, let's say, ice that starts off at negative 25 degrees Celsius here. Time is to the right, and you can also think of time as heat being added, okay? This is why I hate this graph so much, because they use time instead of temperature, or time instead of heat added. But you can assume that the time on the bottom axis here is the same as heat being added. So heat is continually added to our system going to the right. So you start off with ice. It's at negative 25 degrees Celsius. It warms up to point B, where you have ice and water. You'll notice that the temperature does not change. So the idea is that the temperature of ice can go from negative 25 up to 0, but then as you continue to add heat, the temperature of the substance won't change. You have a mixture of ice and water in this region right here. Then once all of the ice is melted, the temperature will then start to increase again from 0 up to 100 degrees Celsius. Notice that the slope of this graph is different than the slope of this graph. That's because it looks like the ice heats up faster than the water does, because ice has about half of the specific heat of water. So the water takes a lot more energy to get it to this temperature. And then now you've got a combination of water vapor plus steam. You have to add all of this energy right here in order to get it to get to pure water vapor. At that point, the water vapor itself can now start to increase in temperature. Okay? And next time we're going to solve a problem with this, but we're just simply out of time right now. I'm going over, so we'll stop. Thanks, everyone. If you have any questions, I'll stick around, and I'll see you on Wednesday. Again, as a reminder... Oh, do we? Oh. Good. Good. I'm I'm thinking of my other class. Yeah, good. Great. You have enough time to do a problem. Great. And I don't have to go too fast either. That's amazing. I should always think I have less time than I'll... Alright. Does this picture make sense? Anyone have any questions about it? Okay. Again, instead of time here, you can think about this as energy added if you want to. Or you can just say that the energy is added at a constant rate. Alright, let's get going. Yeah, we started at 9:45, what was I thinking? Okay, so changes in both temperature and phase. These get pretty confusing, but they still follow the same concepts. A glass contains 0.25 kilograms of omni-cola, which is mostly water, initially at 25 degrees Celsius. So what is that, a glass? So we have a glass. It contains cola. And we know that there's a mass of our cola of 0.25 kilograms. We're going to add ice that starts off at 20 degrees Celsius. So in a separate container over here, what we have is we've got ice cubes that we're going to add. And the question is how much ice. So I'm going to assume that's going to be in terms of mass. We want to know how much ice do I want to add into here. And we know that the temperature of the ice initially, so T initial ice, is equal to negative 20 degrees Celsius. We know that the initial temperature of the coffee, or the cola, T initial cola, is 25 degrees Celsius. And the question is, so a glass contains this, how much ice initially at negative 20 degrees Celsius must you add to obtain a final temperature of 0 degrees Celsius with all the ice melted? Ignore the heat capacity of the glass. So of course we're going to ignore that, because otherwise... we should add the glass in here, honestly. Do y'all want to add the glass in? I want to add the glass in, because that seems stupid to me. We're not going to do that. We're not going to do that. That's too easy. We're gonna say that we know how much is the mass of the glass going to be. Yeah, maybe we shouldn't do that. We're going to do one with multiple substances next. Maybe it's too confusing. I don't want to confuse you all. Let's keep it simple, and we'll do something more complicated next. Okay, so given this scenario, we're going to ignore the glass and say it's just ice being added to this cola. And the question is, what do I need to do? How much mass of ice do I need to add to get a final temperature of the system that's going to be equal to 0 degrees Celsius? Okay? And one thing they do to make this problem even simpler, and it's probably a good idea, is with all the ice melted. So we're going to assume that all of the ice is going to melt, right? All of the ice will melt. That will make this problem considerably easier than it needed to be. All right, so we have to think about what's going to happen here. And I guess we can think about it in multiple steps if we want to. So the next step after this would be that we have our container and it has cubes in it, right? So we take our container here, paste it down here, and we take a few cubes and we place inside of here. So we've added some ice in here, right? So the first heat transfer process that's going to occur here is that am I thinking about this correctly? The temperature of the solution has to get down to 0 degrees Celsius. Before the ice can start melting. Does that make sense? Before the ice can start to melt, the temperature of the system... Oh wait, it's already at 25 degrees Celsius. So this will automatically start melting the ice, right? Kind of, not really. In order for this substance to melt the ice, it has to raise the temperature of the ice up to 0. That's what I was trying to say. Yeah, would you agree? In order for the ice to start to melt, its temperature has to go from negative 20 up to 0. Would you all agree? Okay, so Now that the ice has been added, the first heat transfer process, because these are going to start off at -20. So we have to say that the ice needs to cool down. Or heat up, sorry. It needs to heat up. In order to melt, it has to heat up to 0 degrees Celsius. So that's going to be part of our transfer process here, right? We're going to use the same equation from before. We're going to say that if I sum up all of the individual temperature heat exchanges, that should add to 0. We're going to have the heat exchange associated with the, what is it, cola? We're going to have the heat change associated with the ice, which is going to be going from -20 degrees Celsius up to 0 degrees Celsius. Plus, we're also going to have to deal with the heat change associated with the ice converting fully to water. So those are the things that we're going to need to do, all of those individual pieces right there. So doing that, we're going to need an equation. For the cola, the heat transfer is going to be the mass of our cola times the specific heat of our cola, which is the specific heat of water, multiplied by the change in temperature for that cola, plus for the ice to go from -20 to 0 degrees Celsius, we're going to need the mass of our ice, which is ultimately what we're solving for, multiplied by the specific heat of ice, which we're going to go look up in a table, and then multiplied by that temperature change right there, delta T ice. Plus, we also have to add in the ice changing into water. So we're also going to have M ice times the latent heat of fusion for water. And every piece of this information is either given or can be looked up in the table, except for the mass of the ice, which looks like mice. So let us solve for mass of ice now. Oh, wait, we need to do other things. Let's write out the delta T's. So this is going to be M, C, C, C. This delta T will be... I'm just going to put numbers in because I think it's the easiest thing to do. What's the final temperature of the system? It's 0, right? So we do 0 degrees Celsius minus the initial temperature of this was 25 degrees Celsius. Plus mass of ice, that's what we're solving for. C ice, we can look up in a table. Delta T ice, what would delta T for ice be? Well, it also goes from final temperature of 0 degrees Celsius minus its initial temperature, which is -20. And you'll notice here, Matthew, even though it's negative, I'm still putting in Celsius because we're dealing with a change. Plus mass of ice times the latent heat of fusion of water, which was the 3.34 times 10 to the 5 joules. Right here, again, to find that on the water table, it's right here. 334 times 10 to the 3. And we'll just leave that as LF, but I'll write it over here. LF water is 3.34 times 10 to the 5 joules. LF water. And this is all equal to 0. Sorry, it kind of ran into that picture. I can just scoot this over. So equals 0. Okay, does that equation make sense? Does anyone have any questions before we move on? Because the next thing we're going to do is we're just going to solve for the ice, so the mass of the ice. All right, so let's do that. We need specific heat of ice. I think it's 2090. We're going to go look it up real quick. Maybe it's 2050. Specific heat of ice. Notice it says near. So it's 2100. Ice and water are not the same thing. They have different specific heats. Specific heat of ice is 2100 J over kg degree, or we'll just put Kelvin. All right, so solve for mass of ice. What we'll get I'll just explain what I did here. So the first term, you have MCCC times 0, which is nothing. So you have negative 25, right? You take this entire term and we add it to the right-hand side. And then we basically take all the coefficients for M ice, which is this term, which is C ice times negative 20, so that's positive 20, and LF water, and those are coefficients. We divide them under here. You can work out the math for yourself there. Plugging in numbers. Let me know if you feel like the algebra there is wrong. If you work out the algebra and then you get something different. Okay, specific heat of coffee is going to be 4190. It's not coffee, it's cola in this problem. Do these units make sense? You get joules. Oh, because this is joules over kg. Right? It's joules per kilogram. My bad. That works. Celsius, kilogram, kilogram. We just have joules. Joules per kilogram, we get a kilogram. Yeah, okay. Okay, so what do we get if we calculate this? We might be able to do the other problem, or at least start it. I got 0.07 kilograms. Do you all agree? Okay, I got the same thing. So if we add this much ice, it will all melt, and the final temperature will be 0 degrees Celsius. This problem, as you will see from doing your homework problems, is a vastly simplified version of how hard these can get. And I don't even know if this next one is really going to do justice to it, but we're going to try it. I know in the last time I taught this class that I came up with another example from another textbook, or I got an example from your textbook, because I thought even this one was too easy. Because these problems can get really challenging, and as you know, your textbook doesn't like to use challenging example problems. It's just part of their design philosophy, which I hate, but it is what it is. All right, we don't have much time. We're going to try this one. We have 3 minutes. Hot copper pot of mass 2 kilograms, including its copper lid, is at a temperature of 150 degrees Celsius. So we've got a pot. It is made of copper, and it has a mass of 2 kilograms. It's at a temperature of, we'll call this the initial temperature of the copper, 150 degrees Celsius. So it's really hot. We're going to pour 0.1 kilograms of cool water at 25 degrees Celsius into here. So we're adding water in here. I thought I clicked on the blue one. It's not being nice to me, so we're just going to have to deal with it. We're adding water that has a mass of water that's equal to, what is it, 0.1 kilograms. And it has a temperature initial of water that is 25 degrees Celsius. You then quickly replace the lid so no steam can escape. Find the final temperature of the pot and its contents and determine the phase of the water, whether it be liquid, gas, or a mixture, and assume that no heat is lost to the surroundings. So our question here is, what is the final temperature going to be? Okay, so that no steam can escape, we will put a top on this. Now, it's made out of copper, which means it's going to easily send heat out into the environment, but again, we're going to assume that no heat's lost to the surroundings. Maybe it's insulated in some way. And that is what we want to do. So, we again have to sum over all of the individual heat transfers that occur, and that this should add to 0, okay? Now, in this problem, we're going to have the heat for the copper to go from whatever its initial temperature of the copper is up to the final temperature T that we don't know. Plus, we're going to have the heat transfer from the water. Now the water starts off at 25 degrees Celsius, right? So this is going to be the heat transfer for the water to go from its initial temperature up to whatever the final temperature is going to be. Plus, we're also going to have to deal with the fact that some portion of the water is going to turn into steam or water vapor. And the thing about this problem that's a little bit more challenging is we don't know how much water is going to turn into steam. If we could assume that all of the water turned into steam, that would be very simple. But we can't, okay? In fact, what we ultimately have to determine here is to find the final temperature of the pot and its contents and determine the phase of the water, liquid, gas, or a mixture. This is the most likely possible outcome in this case. It starts off at 150 degrees Celsius here. We add water at 25 degrees Celsius. I think what will probably happen, and this is going to be an assumption, so I'll indicate that it's an assumption. Can I please just pick a different... I hate this program so much. Okay, we're going to assume that the final temperature of our system is... What would be a reasonable thing to assume that the final temperature would be? Answer quick. We don't have much time. We have no time. I'm just going to tell you. 100 degrees Celsius. This is very likely to be the final temperature of the system because if it ends up being the case that there's some water and some steam, you're in a mixture of the water vapor kind of situation, it's probably the case that the temperature of the water is 100 degrees Celsius. Just to remind you, the idea is that if you have a pot that's boiling on a stove and you have a combination of liquid vapor, water vapor coming out, and you have the pot itself, the whole thing is going to be 100 degrees Celsius. So we're going to go with that assumption, and instead of figuring out what the final temperature is, we're going to solve for this. We're going to figure out what the mass of steam that we have is that's left over. All right. So to do that, our equation here is going to become mass of copper times the specific heat of copper. If you need to go, you can leave, by the way, if you have another class right now. All this stuff is obviously going to post it on YouTube. I just want to finish this. Mass of copper times the specific heat of copper times the change in temperature of copper. Let's go ahead and put what that is in here, because we know that the initial temperature of the copper was 150. So this is going to go from, you have to do final minus initial, so it's this minus 150. Plus for the water, we're going to have mass of water, which we know, times the initial temperature of the water, times the specific heat of water, and then times the initial temperature of the water was 25, so we're going to have 100 minus 25. Sorry if this is confusing the way that I'm writing it, but this is final and this is initial, so that's why you end up writing it like this. And then for the water to steam, now what I'm going to write in here is, I'm going to put the mass of steam times the latent heat of fusion of, no, the latent heat of vaporization, they call it, of water, which we can look up in the table. It's like 2E7, 2.256 times 10 to the 6th. That is the latent heat of vaporization of water. And then what we're going to do is we're going to solve for this quantity right here. And if we get something weird, like a number that's bigger than this, or a negative number or something like that, then we're going to have to check our assumption that we made. Our assumption may be wrong. If, in fact, if this answer is, let's say, greater than this, that means that everything converted to steam, and that means the final temperature is not going to be 100 degrees Celsius. Does that make sense? But you got to just go with something in these kind of problems. Otherwise, you'll be lost trying to figure things out. So we do that, and we just solve for the mass of steam here. So we're going to get that the mass of the steam should be equal to all of this junk divided by the latent heat of fusion of, or vaporization of water. So, whoops, didn't mean to do that. I wanted to just copy, paste, take all of that, and then we're going to divide by this. And we'll see if we get a positive number or a negative number, or if we get a number that's greater than the amount that we had to begin with. So let's get down to where we can see everything. So M steam equals. Mass of copper was 2. I don't know what the specific heat of copper is. We'll go look that up. 100 minus 50 is negative 50. I'm going to have to scoot this down. There's just not enough room. Okay. Negative 50 degrees Celsius. Specific heat of copper we'll go look up. Mass of water was 0.1 times specific heat of water is 4190. 100 minus 25 is 75. I don't know, does it look like we're going to get a positive number? The real question is how big is this number? But it's definitely less than water, so I think we're going to get a positive number. And then the bottom we have this huge number, 2.256 times 10 to the 6th joules per kilogram. And looking up specific heat of copper, I didn't go up far enough. It's at the very beginning, isn't it? No, it's right there. Copper is 390. There we go. And if we plug all this stuff together, pretty clear we're going to get a positive number. The question is it greater than or less than the initial amount of water we had? Oh, I did get a negative number. Did I do it wrong? There's a lot of copper. Is it really 2 kilograms? It is. Oh, but I think I did something wrong here. Can anyone figure out what I might have done wrong here? Well, in this case, you're right, but it was actually this piece. Yeah, there's an overall negative sign error that I made. Because in order to do what I did, yeah, I need to have a negative sign, either on the numerator or the denominator, basically, right? Here's the other question. Now, we're going from water to steam, right? This quantity here can be positive or negative, but if you go up, it's positive. Going from water to steam is, yeah. No, there should have been a negative sign here in the denominator. That's the thing I made a mistake on. For the reason that Astro Lover said. Okay, if you do that, you get an answer of 0.003. So M steam is equal to 0.0034 kilograms. Did other people get the same answer? Yeah, you did, okay. So unless I did this wrong, which I easily could have, I did this very fast. I didn't take the time to think about things. Unless I did this wrong, what this tells us is that that's how much steam you have, which means the mass of the water will be 0.1 minus that. So if we take that and we subtract 0.1, you're going to get 0.0966 kilograms of water. So that's the final state of our system here, is that you have 0.0034 kil, and that's what we're supposed to figure out, right? Find the final temperature and determine the phase of the water, liquid, gas, or mixture. So the answer is mixture. And the final thing you would have to do then is to figure out what is the mixture, right? And that's what we did here. This is the kind of thing you'll have to do on your homework. It can be tricky. You sometimes have to make these kind of assumptions. In this case, our assumption was that the final temperature would have been 100 degrees Celsius. And it turned out to be true. Now, what would have made it so that our answer was like something, different? Well, in order for all of the water to turn into steam, what would have to be different? I know we're way over here, but might as well try to be interactive. What would have had to happen if all the water would have converted to steam? What would have had to have been different in our problem? Assuming we leave the water the same amount of water. What would have had to have happened for all the water to be converted into steam? One way to put it is our final answer would have had to have been 0.1, right? So what would we have to do? What about the initial setup we change? No, we wouldn't have one more phase change. There's only going to be one phase change. Now, if all of it, well, copper being a higher temperature, that would do it, right? So if the initial temperature of the copper had been bigger than 150 degrees Celsius, if it had been at like 300 degrees Celsius, then yeah, this quantity may have been a little bit bigger, which may have made the final answer larger. Yep. Because after all, if it turns out that this first term right here is actually bigger than the second term. Yep, that's right. Or we could just have more copper too, right? That would work too. If we just had a lot more copper in our system, that would work as well. So basically, we can't control this, but we can control these two things. Yep. Now, yeah, I think that's all I want to say about this problem. Sometimes you have to make these kind of assumptions. You'll definitely have to be doing that on your homework problems. And I think we'll just stop right there. I will stick around if anyone has any questions. Sorry for going a little bit over, but I just wanted to make sure we actually kind of finish this topic up.